Imagine trying to take a photo of an ant from the top of a skyscraper while riding a bicycle. That's essentially what spacecraft have to do every single day. Whether it's the Hubble telescope capturing distant galaxies, or weather satellites tracking hurricanes, these amazing machines need to maintain incredibly precise pointing in the harsh environment of space. Hey everyone, I'm Eric Hillsberg, and welcome back to Intuitive Aerospace. Today, we're going to take a look at how spacecraft are oriented in three-dimensional space. We've got all of these expensive machines orbiting Earth, exploring other planets, or peering into deep space, and they need to stay pointed precisely in the right direction to do their jobs. A telescope that can't stay focused on its target isn't much use, and those communication satellites beaming your Netflix down, they need to point their antennas. So today, we're breaking down how engineers solve this incredible challenge of keeping spacecraft properly oriented in the vacuum of space. My goal is not to cover every detail of the math and physics involved, but to focus on concepts and intuitions. I've linked a NASA paper below in the description if you want to take a deeper dive. So why do we care so much about spacecraft attitude? Well, it's absolutely critical for almost every mission function. Most importantly, almost all spacecraft rely on the sun for power generation, meaning solar panels need to face the sun to generate electricity. Satellites need to communicate with the ground to transmit data, so their antennas need to point toward Earth or relay satellites. Scientific satellites need to point their instruments like telescopes, cameras, and sensors at their targets. Sometimes, you need to point the hot side away from sensitive instruments. And last but not least, when you fire your thrusters, your spacecraft needs to be pointed in the right direction. Attitude control has enabled some incredible achievements you probably use or benefit from every day. Those navigation apps on your phone rely on GPS satellites. These satellites have atomic clocks which can become out of sync. To maintain their accurate timing, they need to precisely point at ground stations. Without attitude control, your Maps app might tell you you're in the middle of a lake when you're actually on Main Street. To bring high-speed internet to places where it was never available before, services like Starlink use thousands of small satellites, each maintaining precise attitude control to keep their antennas pointed at users on the ground. The 3-day forecast that tells you whether to bring an umbrella is possible because satellites like GOES-16 use extremely stable platforms to take consistent images of developing weather systems. These satellites can stare at exactly the same spot on Earth for years without drifting. To track changes in ice caps, sea level, and atmospheric composition, satellites need extremely stable attitude control to make accurate measurements. And in my last video, we talked about space weather. Satellites measuring solar wind and CMEs must point precisely to ensure proper readings. Attitude control literally shapes how we connect with each other, stay dry, and understand our planet and space around it. Space isn't as empty as you might think. Spacecraft face numerous forces that can throw off their orientation. Because gravity depends on distance, gravity gradient forces pull unevenly on different parts of the spacecraft. Because spacecraft are rarely symmetrical, solar radiation pressure from sunlight hitting the spacecraft causes a moment. Similarly, atmospheric drag for satellites in low Earth orbit can cause a torque. Spacecraft are giant hunks of metal and wires, so Earth's magnetic field interacts with the satellite. And there's also internal disturbances like moving parts or fuel sloshing around. Engineers have to model all of these disturbances and design control systems robust enough to handle them. Before we can control a spacecraft's attitude, we need to know what its current attitude actually is. It's like the old navigation adage: if you don't know where you are, a map won't help you. Spacecraft use a variety of sensors to figure out their orientation. Gyroscopes measure how the spacecraft is rotating, and accelerometers detect small changes in the acceleration and can help determine orientation. These sensors have a lot of noise and other errors, so they're augmented with more precise methods. Star trackers are basically high-definition space cameras that look at star patterns and compare them to an onboard catalog. They're very accurate, but computationally expensive. Sun sensors are devices that detect the sun's position, like how plants track the sun, but with electronics. Earth or horizon sensors detect the edge of the Earth against the blackness of space. Magnetometers measure the Earth's magnetic field direction, and they only work in low Earth orbit. To get these sensors to work together, engineers feed data into a state estimator that combines all of this information to get the most accurate picture possible of the spacecraft's orientation. If you're interested in learning more about state estimators, check out this great video on Kalman filters from my MathWorks colleague Melda. Now that we know which way we're pointed, we need to actually control it. There are two main approaches: passive and active control. Passive control is like a self-righting inflatable punching bag with sand at the bottom. No matter how you push it, it naturally returns to its upright position without any motors or electronic controls, purely through its design and physics. The heavy bottom creates a natural stability that always brings it back to the same orientation. Active control, on the other hand, is like balancing a marble on a small plate. You need to constantly make tiny adjustments with your hand, responding to every little movement that the marble makes to keep it centered. Without these continuous corrections, the system quickly becomes unstable. In space, we often use both approaches together, creating spacecraft with some natural stability, like a punching bag, while still using active systems to make precise adjustments when needed, like occasionally nudging the already stable punching bag to face in exactly the direction we want. Let's start with passive control techniques. These are the clever engineering solutions that require no electricity or fuel to operate. The first spacecraft all use spin stabilization. This super cool method just spins the entire spacecraft like a top. The angular momentum resists nudges that keep it pointed in the same direction. This technique makes science and communication tasks challenging, so it's not as common anymore. This next technique gives us the best of both worlds. In a dual spin satellite, part of the spacecraft spins rapidly for stability, while the other section remains relatively stationary. Imagine a globe that rotates while its stand stays put. In spacecraft like the early GOES weather satellites, the main platform with cameras, sensors, needed to stay pointed at Earth, but they still wanted the stabilizing benefits of rotation. The solution was to have the instrument platform steady, while a separate section spins at about 100 RPM. The spinning section provides gyroscopic stability for the entire craft, while the instruments can remain precisely pointed. Gravity gradient stabilization is an elegantly simple use of physics which turns the disturbance on its head. Earth's gravity decreases with distance, which means that the part of the satellite closest to Earth feels a stronger gravitational pull than the parts further away. For elongated satellites, this difference in force naturally orients them vertically, with one point pointing toward the Earth and one point pointing to space. Many small LEO satellites use this by deploying a boom or a tether to create an elongated shape. This passive technique is perfect for communication satellites and Earth observation missions, where you want one end consistently pointing at Earth without using any power or fuel. The longer the satellite, the stronger the stabilizing effect becomes. And then there's magnetic stabilization. This technique turns Earth into your attitude control system. By placing permanent magnets or magnetorquers on board, satellites can interact with Earth's magnetic field just like a compass needle aligns north. The satellite essentially becomes a giant space compass, maintaining a consistent orientation relative to Earth's magnetic field lines. This method is especially effective for small CubeSats in low Earth orbit, where Earth's magnetic field is strong. Engineers can combine magnets with small dampers to absorb oscillations, allowing the satellite to settle into a stable orientation. These are the most common passive techniques, but new ones like solar sails have become increasingly popular. The advantages here are simplicity and reliability. No moving parts to break, no fuel to run out, but limited in accuracy and flexibility. You can't easily change where a passively controlled spacecraft is pointing. For missions requiring precise pointing, active control is required. These systems constantly sense and correct the spacecraft's orientation. Magnetorquers are electromagnetic coils that generate a magnetic field in the spacecraft, which interact with the Earth's magnetic field and create a moment. They produce small torques and require no propellant. They're arranged in groups of 3, aligned with the 3 axes of control. Primarily, they're used for momentum management rather than rapid maneuvers due to low torque outputs. Thrusters, small propulsion systems, use cold gas, monopropellants, or bipropellants to create precise torques. They provide high control authority, which means they're good at their job, but they consume the already limited propellant and risk instrument contamination. These kinds of systems are pretty much required on larger spacecraft. Reaction wheels are precise flywheels which can be spun to generate torques and capture momentum. Typically, they're arranged in groups of 3 or 4 on magnetic bearings. They can achieve extremely precise accuracy, that of 0.001 degrees. Their ability is limited due to momentum saturation. They can only spin so fast, but they also create some microvibration issues. Control moment gyroscopes, or CMGs, are constant speed flywheels mounted on gimbals that create torque through reorientation rather than speed changes. They can generate 200 times more torque than the equivalent reaction wheels, enabling rapid slewing with efficiency. Pyramid configurations provide redundancy but require complex steering laws. They're used on the ISS and Agile imaging satellites. As I just mentioned, reaction wheels can only spin so fast before they reach their limits. As they absorb the angular momentum from external disturbances over time, they eventually saturate, meaning they can't spin any faster. When this happens, we need to offload or desaturate the wheels by using another system, usually magnetorquers or small thrusters, to counteract the external forces while spinning the wheels back down. This is called momentum management, a critical aspect of attitude control system design. All in all, active systems provide precise pointing in any direction, but require power, experience mechanical wear, and in the case of thrusters, deplete propellant reserves. Spacecraft rarely rely on a single control technique. Instead, they employ sophisticated control hierarchies that integrate multiple methods to maximize efficiency, reliability, and mission performance. Modern spacecraft utilize a strategic integration of passive and active techniques. Passive systems like gravity gradient or spin stabilization establish fundamental orientation stability with minimal resource consumption. Active systems, like reaction wheels and CMGs, provide fine adjustments for accurate pointing during critical operations, and backup systems automatically engage during anomalies, progressively falling back to simpler, more reliable control methods like gravity gradient. And different control techniques activate based on mission phase requirements. Science observation mode is the highest precision mode utilizing the full active control suite. Reaction wheels or CMGs maintain ultra-stable pointing. This mode prioritizes precision over efficiency, with all vibration compensation and isolation systems active. In safe mode, the spacecraft's self-protection configuration is activated, typically during anomalies or emergencies for the spacecraft. They place the solar arrays pointing towards the sun, they position the antennas towards Earth, and they deactivate all of the non-essential systems to conserve power. They fall back to the most reliable, often passive, control methods and use their wide-field sensors rather than the precision instruments. They can also maintain their thermal balance to protect sensitive components. For large or deliberate orientation changes or orbital adjustments, maneuver mode is activated. This mode transitions from reaction wheels to thrusters for large slews. It implements specialized guidance algorithms for efficient reorientation. And sometimes you sacrifice your pointing accuracy for maneuverability. You're going to execute pre-calculated burn sequences so you have predictable outcomes. The initialization or recovery configuration used after launch, deployment, or system resets is called acquisition mode. During this phase, the spacecraft sequentially identifies reference objects like the sun, Earth, and stars, and it establishes its initial attitude estimate. It dampens deployment-induced rotations, and gradually transitions from coarse to fine sensors. This systematically activates control systems in a predetermined sequence. The Hubble Space Telescope exemplifies this approach with modes including coarse sun pointing, a basic safe mode, fine lock for precise observations, and various acquisition modes that systematically build up pointing accuracy. By seamlessly transitioning between these modes, spacecraft can optimize the trade-offs between pointing accuracy, power consumption, and system reliability throughout all mission phases, from critical science operations to emergency recovery scenarios. Learning from failure is a huge part of engineering, and there have been some fascinating cases where attitude control problems taught us valuable lessons. When first deployed, Hubble experienced a problem called solar array jitter. Every time the spacecraft moved from Earth's shadow into the sunlight, the temperature change caused the solar arrays to expand, creating vibrations that disrupted observations. Engineers had to develop new control algorithms to compensate for this unexpected disturbance, and almost immediately, the James Webb Space Telescope team began designing around Hubble's limitations. In 1998, the Solar and Heliospheric Observatory, or SOHO, lost attitude control during a routine maneuver and went silent for weeks. The spacecraft was spinning, but couldn't point its solar arrays at the sun and was quickly losing power. In an incredible rescue operation, engineers had to figure out how to regain control of the spacecraft, and they could barely communicate with it. America's first space station, Skylab, lost part of its thermal shield during launch, causing attitude control problems that nearly doomed the mission. Without proper thermal protection, the station was overheating. NASA had to rapidly develop a makeshift sun shield and new attitude control procedures to save the station. The Kepler Space Telescope lost 2 of its 4 reaction wheels, which would normally have ended the mission, but engineers devised an ingenious solution using solar radiation pressure as a virtual reaction wheel to continue the mission in a modified form called K2. These cases show how robust design, redundancy, and creative problem solving are essential in spacecraft attitude control. They've helped engineers design better systems with each generation of spacecraft. So there you have it, spacecraft attitude control in a nutshell. From the passive elegance of gravity gradient stabilization to high-tech precision of reaction wheels, and everything in between. The next time you see a beautiful image from a spacecraft telescope or get a satellite TV signal, remember the incredible engineering that keeps those spacecraft pointed exactly where they need to be. If you're interested in learning more, I've linked a NASA paper in the description below. It goes much deeper into the mathematics and engineering principles we've discussed today. Thanks for watching, and I hope you enjoyed this video. Please like and subscribe below for more aerospace content, and let me know if there's any topics you'd like me to cover in the future. See you next time.